From our previous discussion on the kinetic theory of gases, the postulates that we had derived, the postulates that we have given, and the equations derived from that, leading us to the pressure of a gas, which is of the form P equals to 1 upon 3 times of the P is equal to 1 upon 3 times of the total mass m over the total volume V times of c squared, which leads us to 1 upon 3 multiplied to the density times of c squared, where c is the root mean square velocity that is of the form c is equal to root over of 3p over rho, which is obtained from this equation that we have written right above. And also we deduced the relation of the pressure with the energy density, which is pressure is equal to 2/3 of the energy per unit volume. Now all of this further leads us to some more important results from the kinetic theory, that is the kinetic interpretation of the temperature. That is what we are going to start off this video with. So kinetic interpretation of temperature from the relation that we have, that is for PV is equal to 1 upon 3 mc squared. We have this relation with us, and also we have from the gas equation that PV is equal to this relation is obviously from this relation. I hope you get it. And PV is equal to RT for a single unit mole of a gas, and therefore we can equate the right hand sides of the equation, and the right hand sides of the equation, equating them, would yield 1 upon 3 mc squared is equal to RT, and that gives us c squared to be equal to 3RT over m, or we know that c squared is directly proportional to the absolute temperature, or c is directly proportional to the root of the absolute temperature. And what that would essentially mean is that a supply of heat to a body results in a rise of temperature and hence an increase in the RMS velocity of the molecules. This interpretation of temperature is in terms of the velocities of the molecule is what we call as the kinetic interpretation of temperature. Now for the value T is equal to 0, obviously C will be equal to 0. That means the root mean square velocity is possible, and that can be possible if we consider the case where C is equal to, as C is equal to the root over of C1 squared, C2 squared, right up to n number of molecules, Cn squared whole divided by n, that is the root of the root of the mean of the square terms of the velocity of the individual molecules. And as this goes to 0, all of the molecules, that is C1, C2 and C3, the velocities of all the individual molecules must vanish. That is, at absolute 0, which is the temperature over here that we have mentioned, all the molecular motion must cease. So that is how we interpret the case of temperature, the kinetic interpretation of temperature, that is available to us only through the postulates of kinetic theory of gases and from the equations thus derived from that. And the rest of the cases of discussion are as follows, where we obtain the kinetic energy per mole of a gas. Now this equation that we have over here, that is right from this equation at the top. So 1 upon 3 mc squared is equal to RT as discussed earlier, and if we take 2/3 of it, then or 3/2 of it, so we get half mc squared on the left, and we are left with 3 upon 2 RT. Now the half mc squared is the kinetic energy per mole, because we have that is the kinetic energy per gram mole, where m is the molecular weight. and because m is the molecular weight, that is why it is kinetic energy per gram mole. Now the kinetic energy per gram of the gas will be equal to, when we divide the above expression, that is half mc squared, by m, that is the molecular weight. So that will give me the kinetic energy per gram, and that comes out to be equal to 3 over 2 R over m times of T. The R over m is taken as small r, which is the gas constant for 1 gram of gas. And finally, we obtain the kinetic energy per molecule of the gas, which is the n number of molecules. So we divide it through n, and also the right hand side of the equation is RT over n. That changes to half of small m, that is the molecular weight per molecule, and K being the Boltzmann constant, where we have that to be equal to the universal gas constant R divided by the total number of molecules. So that gives the kinetic energy per molecule of the gas. Now there are some important things that we must consider in these equations that we have just obtained. The first being that the kinetic energy of 1 mole of every gas is the same if they are maintained at the same temperature, because T remaining constant, the R is always the universal gas constant. So for a constant temperature, the kinetic energy per mole of every gas will be the same. Also, the kinetic energy per gram of the gas depends, that is the third part that we are discussing now. The kinetic energy per gram of a gas depends on the nature of the gas, even if their temperature is the same, because we have that to be divided by the molecular weight, and that is different for different gases. So specifically for the given gas. And the final thing is the kinetic energy of 1 molecule of all the gases at same temperature has to be the same irrespective of their nature, because on the right hand side, as you can see, for the temperature remaining same, the rest of the term, that is the Boltzmann constant, that is a constant value, so that remains the same every time. And that is why we conclude that for all the kinetic energy of 1 molecule for all the gases at same temperature must be the same, and irrespective of their nature, because there is no molecular weight involved in that case, as in the third expression or the third bit. So now we'll be moving over to the explanation of the gas laws that we had studied, and that will be all those laws will be explained by the concept of kinetic theory of gases. The postulates that had been laid down and the equations thus obtained will help us understand those gas laws. So let's move over to that in the next page. So here we are about to explain the gas laws on the concept of the kinetic interpretation of temperature. And what it says that in case of kinetic interpretation, what we have learnt is that c squared, that is the square of the root mean square, is directly proportional to the temperature absolute value, or we can just lay down as c square is equal to some constant times of T, constant of proportionality. Now this relation can be used to explain the different laws as follows. To start off with Boyle's law. The Boyle's law stated that the pressure is inversely proportional to the volume at a given temperature, and let's see if we can get to that. So we have PV to be equal to 1 over 3 mc squared, and that is equal to 1 over 3 small m times of AT. Why the small m? It's actually capital M. So m times of AT, and AT has come up in place of c squared. So this leads us to PV to be a constant for T being constant, and that results in P to be inversely proportional to V, which is the Boyle's law given at a constant temperature. So we have derived the Boyle's law by using the kinetic interpretation of temperature. Remember, this is for a given ideal gaseous system, so m is a constant there for a given gas, and as a result of that we obtain this equation, or we derive the law. As for Charles' law, we have P to be equal to 1 upon 3 m over v, the v taken to the right hand side, c squared, and we have 1 over 3 m over v times of at, and actually we must have taken the v onto the right, p onto the right hand side instead of v. And so for a given gaseous system, for m and p, the pressure remaining constant, we get v to be directly proportional to the temperature, which is the Charles law. In the third case, the Gay-Lussac's law that we had given for pressure, with pressure being equal to 1 over 3 m over v, now the v can be taken to the right hand side, and for m and v being constants, we have pressure to be directly proportional to, in case of c squared, we have the at again, and a is a constant, so pressure is directly proportional to the temperature, and therefore we have the Gay-Lussac's law for pressure. And as for the Avogadro's law, taking P1 and P2 to be pressure of two different gases contained in the same volume or having a common volume, so we have the right hand sides of the equation for P1 and P2 being similar. The right hand sides of the equation with 1 by 3 is taken constant. We end up with m1c1 squared m2c2 squared, and what that leads us is that m1 will be equal to m1 times of n1, the number of moles, that is in case of the first gas, with the mass of the molecules m1, and m2 being the mass of each molecule, and n2 the number of moles. Now if we multiply a half on both the sides, we obtain the kinetic energy term, and the kinetic energy per molecule in any gas is a constant, because this is considering the single molecule with m1 and m2 being their masses. So for any single molecule, we have taken the number of moles outside the bracket. So single molecule of the first gas, the kinetic energy of that, and the single molecule of the second gas on the right hand side with the kinetic energy of that, and that will be equal to 3 by 2 over kT, as we had obtained kinetic energy per molecule of a gas. And that 3 by 2 on both the sides, they cancel out each other, and we end up with Avogadro's law, which states that for a given for all the temperature and all the other conditions remaining constant, the number of moles or the number of molecules for two gases will be constant for sure. So that now brings us to the end of our discussion. I would prefer you to try the derivation of the Graham's law of diffusion by using the concept of the kinetic interpretation of temperature, and give it a shot, give it a try. Then you would get to know whether you have understood the topic in the proper way or not. In case you find it difficult, you can tell me, and I'll provide it with you. Probably in the next video I'll be doing it voluntarily myself. So till then, thank you for watching.